In this video and in tomorrow's video, we're going to talk about the final material of this course, which is about the so-called conic sections. The conic sections, this is a collective term for the collection of shapes, parabola. All the parabolas are an example of conic sections. Circles are in the group which is called the conic sections. Ellipses is in the group called a conic section, and hyperbolas are in the conic sections. Sam, put an image on the screen right quick. They are called conic sections because they are equivalent to the shapes that you get if you take a double cone and slice that double cone with a plane. By slicing that double cone with a plane in different ways, you can get the parabola, you can get the circle, you can get the ellipse, and you can get the hyperbola. Parabolas and circles are usually covered in algebra and pre-calculus 1. Ellipses and hyperbolas are usually covered in pre-calculus 2. Today, we're going to look at the graph of an ellipse and look at the relationship between the ellipse's graph and its actual formula. We're going to calculate something called the eccentricity of an ellipse, and we're going to locate something called the foci of an ellipse. So an ellipse is basically just a circle that has been stretched out a little bit in either the x or the y direction. And one of the quintessential examples of ellipses in the real world is that if you look at a planet which is orbiting the sun, or if you look at a moon which is orbiting a planet, the movement of the planet around the sun, the movement of objects in orbit, is an elliptical movement. They move in an elliptical pattern.
I'm escaping to the one place that hasn't been corrupted by capitalism. Space!
So to begin with, let's talk about what the equation of an ellipse looks like. Suppose you have an ellipse centered at the origin, a location that we are describing by x and y equals 0. And the ellipse passes through the points where if y is equal to 0 and we're on the x-axis, we're going to call those intercepts positive a0 and on the flip side, negative a0. Now, where does the ellipse intersect the y-axis? We're going to call those points b0 and negative b0. So the ellipse that's being described by the following equation might look something like this. This would be the image of the ellipse in the case that b is larger than a and the stretching is larger in the y direction than it is in the x direction. But it could just as well be that a is larger than b and this ellipse is stretched out more horizontally. The formula for the ellipse passing through these 4 points is given by x squared divided by a squared plus y squared divided by b squared is equal to 1. As a quick example, suppose that we were going to sketch the graph of the equation x squared over 16 plus y squared over 4 equals 1. Now if I compare that with the previous formula, what we're saying is that 16 is taking the role of a squared and 4 is taking the role of b squared. So that means if I assume that a and b are positive numbers, which is traditional, that a would be equal to 4 and b would be equal to 2. So this would be the ellipse that stretches 4 units in the positive and negative x direction and which stretches 2 units in the positive and negative y direction. So if I were just going to roughly sketch a graph of this ellipse, it would look something like this. We can use this formula to go backward as well. Suppose that we had the ellipse which is given in the following image, which stretches to plus and minus 4 in the y direction, plus or minus 2 in the x direction. In this case, the a squared would be equal to this x equals 2 squared. So a squared would be equal to 4. And b squared would be equal to this y coordinate squared. So b squared would be equal to 16. So this ellipse, which stretches a little bit further in the y direction than it does in the x direction, is going to correspondingly with the largest number under the y instead of the x. If I divide y squared by a larger number, then y itself has to be bigger in order to make this equation true. Now, ellipses are basically just slightly stretched circles. And if we want to figure out exactly how stretched an ellipse is as compared to a circle, we use a number which is called eccentricity. The eccentricity of an ellipse is a measure of how different that ellipse is from a circle, how stretched, how squashed the ellipse is compared to a normal circle. For example, in this image, we have the ellipse, which is equal to x squared divided by 1 squared plus y squared divided by 1.1 squared. So the number underneath y is only a little bit larger than the number underneath x. And therefore this ellipse is only stretched out a little bit in the y direction, a little bit longer in the y direction than it is in the x direction. I would expect this ellipse to have a small eccentricity. If I change the number under y to something like 25, however, well now I have to zoom way out to even fit this ellipse into this picture, because the difference between number under x is so vastly different from the number underneath y. The x stretches from positive to -1, but the y stretch from positive to -25 because we have a 25 squared under the y squared. So this is an ellipse that I would expect to have a large eccentricity because it's quite different from a circle. It's very stretched out compared to a circle. So what is the exact formula for the eccentricity of an ellipse? Our intuition suggests that the eccentricity is going to be relatively small if the values of a and b are close to each other. And there are two different formulas depending on whether a squared or b squared is the larger number. If a squared is the larger number, then the eccentricity is equal to the square root of 1 minus b squared divided by a squared. If a squared is the larger number, it is the quantity which is in the denominator in this formula. Whereas if b squared is the larger number, the formula is almost the same, except we put b squared in the denominator. The goal is always to divide by the larger number. Now, it turns out that the result of this calculation, the result of the eccentricity, is always going to be equal to a number which is between 0 and 1. Now, if the eccentricity is close to 0, it is a low eccentricity, then your ellipse is vaguely circle-shaped. And if your eccentricity is close to 1, then your ellipse is quite stretched. For example, let's calculate the ellipse, the eccentricity of the ellipse, x squared divided by 16 plus y squared divided by 4 equals 1. So the 16 is our a squared, the 4 is our b squared, and we can see that a squared is the larger number. So to find the eccentricity, I'm going to take 1 and take away the b squared, the small number, divided by the a squared, the big number. would be equal to approximately 0.87. So relatively close to 0 to reflect the fact that it's relatively stretched out. Now suppose that I swapped the values of a squared and b squared. This time a squared is 4 and b squared is 16. Because b squared is the larger number, I have to use the formula that has b squared in the denominator and a squared in the numerator. So I end up getting exactly the same eccentricity. That's because the ellipse in this exercise and the ellipse in the previous exercise are stretched by the same amount. It's just that the first ellipse is stretched horizontally, whereas the second ellipse is stretched more vertically. Now, if we go back to the case of an elliptical orbit of a planet around the sun,
Space!
for example, Earth's orbit around our solar system's sun, then you can first of all observe that the eccentricity of the orbit is rather low. This image is quite exaggerated, showing a fairly stretched elliptical orbit, but the truth of it is closer to what is in this image. Another thing that's interesting about the orbit of planets around the sun is that the sun is not located in the direct center of the ellipse. The sun's position is slightly offset from the center. And we give a special name for the location of the sun in the planet's orbit. The location of the sun is called a focus point, or simply a focus, for the ellipse. So we have a mathematical formula that can be used to locate the focus points of the ellipse with the formula x squared over a squared plus y squared over b squared equals 1. Now, first of all, there are going to once again be two different formulas depending on whether the ellipse is horizontally stretched or vertically stretched. Let's first consider the case that the ellipse is horizontally stretched. Therefore, a squared is the bigger number. If a squared is the bigger number, the foci are located horizontally.
Foci. Foci.
The focus points are positive C0 and negative C0. Now, what is the value of C? C can be found by taking the square root of the number a squared, the larger quantity, minus b squared, the smaller quantity. Now, if b squared is the bigger number, and your ellipse is stretched in the vertical direction, in this case, the foci are located vertically along the y-axis. 0c and 0 negative c, where the value of c is equal to the number where b squared, the larger quantity, is in front, and we're going to take away a squared. Let's see a quick example. Let's go back to our ellipse. X squared over 16 plus y squared over 4 equals 1. And this ellipse is stretched out in the horizontal direction. So the foci will also be located along the horizontal axis. Here's just a rough sketch. So to find the exact position of the foci, I'm going to take C and set it equal to the a squared, which is 16, minus the b squared, which is equal to 4. So C is equal to the square root of 12, which is approximately equal to 3.5 units. Now let's plot these two focus points, one of them at negative 3.5 over negative 3.50 and one at positive 3.50. Let's plot those 2 points and the ellipse on Desmos to see what this picture looks like exactly. So here is a visualization of the ellipse represented by x squared over 16 plus y squared over 4 equals 1, as well as the two focus points that we calculated, both of which are horizontally positioned because the ellipse is horizontally stretched. So if the red curve represented the orbit of a planet, then the two focus points would represent the two possible locations of the sun in that orbit. Now this, I think, would not realistically represent any real-life orbit though. Generally speaking, if you have an ellipse with a large eccentricity like this one, the focus points end up relatively close to the ellipse itself. And as a result, if your planet's over here, really close to the sun on the left side of the ellipse, everybody's going to get burned up in that case, and everyone's going to freeze on the opposite side. So that's one of the reasons why, especially for livable planets like Earth, we tend to see relatively small eccentricities, so we never end up too close to or too far away from the actual sun. So to finish up our lecture on conic sections, and to finish up the final lecture of the course, let's go ahead and talk about hyperbolas. State the definition of a hyperbola. We're going to be able to identify its equation and its graph. We're going to be able to sketch a graph of a hyperbola using its equation, and we're going to find the focus points of a hyperbola, similar to what we did with ellipses. We are once again returning to space to look at applications of hyperbolas. A gravitational slingshot involves launching an object toward a sun or planet or star or something, or a black hole or something like that, with the intention of the planet exerting gravitational force on the object, not to pull the object into the sun, but to sort of whip the object around the sun and send it off in another direction. Now, the hyperbola is the name of the curve that is traversed by an object as it goes through a gravitational slingshot maneuver. You've seen gravitational slingshots before, probably at least once. I think they've come up in Interstellar, almost certainly in at least one Star Trek episode. You can do it yourself if you play Outer Wilds. This is one of the core mechanics of the game Luna's Wandering Stars, for example. Now, a hyperbola is very similar to an ellipse, except instead of having a plus sign between the two fractions, you have a minus sign between the two fractions. Now, the graph of an ellipse could be described as a slightly stretched out circle. The graph of a hyperbola, though, is relatively unique. The graph of a hyperbola resembles a pair of curves, either a pair of vertically symmetrical curves, similar to what you can see in this blue sketch here, or a pair of horizontally symmetrical curves, as in this green sketch here. Now these curves, as you get further and further away from the origin, approach a pair of crossed lines. Those crossed lines can be squeezed directly in between the two curves in your graph. And these curves and these two lines have the equation y is equal to positive b over a times x. That's the line with the upward slope. And y equals negative b over a times x. That's the line with the downward slope. Now, what am I talking about when I say b and a? I'm talking about these numbers underneath x squared and y squared in your equation. B would be the square root of whatever number appears under the y squared in your equation. A would be the square root of whatever number appears under the x squared in your equation. Now, how can you tell whether the curves are going to be vertically symmetrical, or horizontally symmetrical? You can tell depending on whether your equation has the y squared first and then the x squared is being subtracted from that, or if your equation has the x squared first and the y squared is being subtracted from that. If your equation has the y squared first, then that's the case where the curves are vertically symmetrical. Y is the vertical component. If y squared is first, then the curves are vertically symmetrical. Whereas if the x squared is first and you're taking away y squared, that's the case where you get the horizontally symmetrical curves. Okay, so let's go ahead and let's quickly sketch the graph of the following hyperbola. In this hyperbola, we have x squared over 16 minus y squared over 4 equals 1. And I'm expecting them to be horizontally mirrored. Horizontally mirrored because in my equation x squared comes first. So I'm expecting something, roughly speaking, that looks like this. I'm also expecting to be able to squeeze in a pair of crisscrossed straight lines. Crisscross straight lines who, if I wanted to reference the fact above, would have the equations y is equal to plus or minus b is equal to 2 because b is squared is equal to 4, and a is equal to 4 because a squared is equal to 16. So these two crisscross lines would have the equation plus or minus 2 over 4 times x, or y equals plus or minus 1/2 x. Now let's graph this hyperbola on Desmos, and let's check and see if those facts are satisfied. This is the true and real hyperbola. Now let's graph the two slanted lines y is equal to plus or minus b divided by a. And we can see that we can just sort of barely squeeze those crossed lines in between these two curves here. As a matter of fact, the red curves are going to get closer and closer to the crisscross lines as we move out away from the origin. So the hyperbolas asymptotically get closer to the crisscross lines as we move away from the origin. Now what if we reversed the roles of x and y, and we had y squared over 4 in the lead, and we were subtracting x squared over 16 in the back? Then the result of doing that is that the hyperbolas are going to be vertically symmetrical instead of horizontally symmetrical. So here we are on Desmos, and we can see the graph of the hyperbola that has a y squared over 4 minus x squared over 16. Because the values of b and a have not changed, b is still equal to 2 and a is still equal to 4, we still get exactly the same equations for the two crisscross lines. Y is equal to positive 1/2 x and y is equal to negative 1/2 x. To finish up the material on conic sections, let's briefly discuss the concept of focus points for hyperbolas. Now, in terms of the gravitational slingshot maneuver, the significance of the object which is exerting the gravitational force is that it is located at a position which is referred to as a focus point of the hyperbola. So there are two different varieties of hyperbola, one of which is horizontal and one of which is vertical. In the horizontal case, the x squared term comes first, and the y squared term is being subtracted from that. And in this case, the focus points are correspondingly also located horizontally at positions which are called C0 and negative C0. The value of c can be found by taking the square root of a squared plus b squared. Now, if the hyperbolas are vertically stacked, where y squared comes in the lead, then the difference is that the focus points will also be vertical. The x's will be 0 and the y's will be equal to either plus or minus c. The c value, however, the formula for it is exactly the same. So let's do a quick example and let's find the focus points of the hyperbola y squared over 4 minus x squared over 16. So I'm going to first of all I'm going to notice that this hyperbola is vertically stacked. So the focus points are also going to be vertical, 0c and 0, negative c. Now, what is the actual value of c? That can be found by taking the square root of the sum of the a squared value and the b squared value, these two numbers under x squared and y squared. So that's equal to the square root of 20, which is approximately equal to 4.5. So the focus points are located at 0, 4.5 and 0, negative 4.5. So here I am back on Desmos, and I've graphed the vertical hyperbola given to me in the problem, as well as the two focus points that we have calculated. So for example, if I wanted to do a gravitational slingshot maneuver, I could launch the object so that it had a trajectory maybe right around here in this bottom left corner. And as it got closer to the object represented by this blue dot, the blue dot's gravitational force would begin to bend the trajectory of the object and then ultimately launch it in this other direction toward here in the bottom right. Now that concludes our discussion on ellipses and hyperbolas. Now I have focused on my personal favorite applications of these two conic sections, which are space related, because space is awesome. But these are not the only applications of ellipses and hyperbolas. If you go to Math Stack Exchange, there are a bunch of archived forum posts with many other applications of these conic sections, which I encourage you to look at if you're interested. Here's one more that I ran across that I thought was kind of interesting. So suppose that you have a table lamp with a circular or cylindrical lamp shade. Look at the shadow that is cast on the wall by this lamp. If I turn the contrast way up, you might be able to see it a little bit better. This would be the upper half of a vertically stacked hyperbola. It has that same shape.